Welcome to this session on graphs. Our next topic is graphs, and practically this is the second last topic of the course. So after graphs, we'll be talking about trees and planar graphs, which are also types of graphs. And then, if time permits, our last topic will be number theory and cryptography. So let's start with the basics of graphs. So you might have seen these kind of graphs in your previous math courses. So these are the graphs which are either known as charts or like in mathematics, we call them graphs, but they are graphs of continuous math. In discrete math, a graph looks like this figure, which you can see on the screen. Uh, it has two kinds of components. Then there are those blue dots, and then there are these red lines between those dots, which are essentially connecting those dots uh, with each other. So these two terms are the fundamental building blocks of graphs. So we call them vertices. These blue dots are called vertices. Singular is vertex, and vertices are connected by lines. These line segments are called edges. So vertices and edges are the common terms which we'll be using again and again in our all discussions related to graphs. Most of the time, what we do is that we assign some names to the vertices so that we can distinguish one vertex from the other, and it helps us to refer to a particular vertex. And edges can be named separately, but once the vertices have been named, then we can treat a pair of vertices as a possible edge. So, for example, if you look at the red line, AD is an edge, where A and D are separate vertices. So formally, a graph is composed of two sets. One set is set of vertices. We'll notate it as capital V, and the other set is set of edges. We'll notate it as capital E. So V and E are the common terms which we use in graph theory. And we have already talked about that each edge can be represented as pair of vertices. So if you look at this particular figure which we have on screen, so if you pick one vertex from A to B, sorry, if you pick one edge from vertex A to vertex B, the same edge also refers as an edge from B to A. So essentially, if the directions are not mentioned on the graphs, we call them undirected graphs. So an edge is going to be an unordered pair. But if the graph is directed, which we'll see in a while, then we'll have to be very careful about the order of the elements within that pair. So for this particular example, you can see that graph is composed of two sets, V and E. V contains four vertices and E contains four edges, but each edge is represented as an ordered pair. But because the graph is undirected, the directions are not important at this stage, so we can write those edges in any order. And we'll have to be more careful about the ordering of elements within a pair when we notate a directed graph using these ordered pairs. Graphs have large number of applications in our real applications. So for example, you can see some names like network analysis, link analysis, social network analysis. These are the common interchangeable terms which people use. And different applications are modeled as graphs at the back end, and then we apply graph theoretic principles to solve those problems. And practically, we solve the problems of those domains which are being modeled as graphs. So graph is a discrete structure. So we can model a real world problem of a particular domain using graphs, and we'll see some examples. But as you go along in your next course of data structures, you'll be studying graphs as a data structure. So graphs model a real world application, but at the same time, you can use graphs to store data in a particular fashion, and that helps us to process the data using different graph theoretic algorithms. So for example, a graph can be used to model internet, some telecommunication network, or some power distribution network. graphs have a lot of applications within software programs themselves. So for example, function calls are connected from, so one node can be a function, it calls another function, and recursion is beautifully modeled as a special type of graph, which is called tree. We call it recursion tree. Web in itself is a huge application of graphs, where we have on one particular page, we have different hyperlinks. From those links, we can land to different pages. So one page or one website has connectivity with some other websites using hyperlinks. So hyperlinks essentially serve as edges, and those pages themselves are the vertices. Or in the context of research, one research paper cites some other research papers, and those research papers cite further research papers. So there's a pool of different research concepts or research papers which are connected through each other using citation networks. Transportation networks are like very common example of graphs. For example, like air transportation, highway transportation, or railway transportation. So, for example, if you think of air transportation, you might have heard of Copilot or Autopilot to fly a plane. So, because your entire route and map is modeled as a graph, so we can apply graph theoretical algorithms and design sophisticated algorithms which can actually help the pilot to fly a plane from one place to another one. One common example that we see in our daily lives is Google Maps. So different, like if you have to travel from lunch to, let's say, railway station, so we set our source, our current place, and our destination, and then using graph theoretic approaches, our algorithms, our programs, more specifically these Google Map applications, they actually suggest us different possible routes which we can opt for from one place to another one. And those kind of things have served as the building blocks in these self-driving cars. Social networks are another like very fancy and beautiful application of graphs. So for example, you can think of Facebook or Twitter or any social media platform. So if you think of Facebook, so one person is connected to another person through a link of friendship. So one person might have subscribed certain pages. So those are some other kinds of connections. And each entity, each vertex is essentially either a person or some page or group of that particular social media platform. And so, for example, if you like think little more about social network platforms, you might have seen already on Facebook or other platforms that sometimes you receive suggestions for friendship. So some background algorithm actually computes the possibility of adding an edge between your node and node of someone else based on some certain similarities. Similarities could be some common friends, common interests, maybe common geographical location, and so on. You might have heard of the news last month that the Nobel Prizes in physics as well as chemistry have been given to people who have done something related to artificial intelligence. So if you like recall the one which was given for chemistry, so the guy who was there was a group of I think 2 persons who were awarded with the Nobel Prize in chemistry. So the core work actually involved intelligent applications of graphs to model some protein structures and discovery of different new structures which are like helpful in drug discovery and disease diagnosis. So these days, bioinformatics, computational biology, and those kind of fields are intensively using graphs as a foundation stone to model different biological and related problems using graphs, and then addressing those problems using graph theoretic algorithms and graph theoretic approaches. Economics has a lot of applications of graphs, and then there are many more. So one application which is not mentioned on the slides is in the current era, you might have heard of the notion of deep learning or machine learning. So the building block in deep learning is a neural network. The neural network is essentially a graph. So in AI and in machine learning, graphs have a lot of importance. So as you go along in your CS journey, probably graphs will be one of the most attractive choices or attractive building blocks which you will see, you'll use, and you will apply to solve different kinds of problems. We're moving a little further in introduction of graphs. So we have already seen that graphs are composed of vertices and edges. Graphs could be undirected or could be directed. So one type is undirected simple graphs. When we say undirected, that means there is no direction on edges. And practically it means that AB and BA are treated as the same edge. Or more specifically, when AB and BA are being treated same edge, then we say that the pair is not really required to be an ordered one. So order of the graph is number of vertices. So cardinality of set V is n. We call it order of the graph. The second term which we use in graphs is the number of edges. So essentially it's cardinality of the set E. So the first ICP which will film online for this session, what is the maximum possible size of G of order n? So the question is on maximum possible size. So try to draw some examples, pause the video over here, try to come up with the answer, and then you can match your answer with the one which you'll see on the slide in the next moment. So hopefully you would have paused the video and figured it out on your own. So if you think of a graph, every vertex is connected with every other vertex, and that's the kind of edges which we'll have in the undirected simple graph. So more specifically, we are talking about subsets, all possible subsets of vertices. When we say subsets, that means order does not matter, and each subset is of size 2. So number of subsets of size 2 are n choose 2. The one comment which we didn't talk much about was that why do we call them simple graphs, and this will become little more clear when we talk about these two types of graphs, pseudographs and multigraphs. So pseudographs are the graphs where there could be a loop on the vertex itself. So there's an edge from a vertex to itself, which means that we can have an edge AA. So those are not the common types of graphs, but sometimes for certain applications we might need that. So in general, whenever we'll be talking about graphs, so we will not include pseudographs in our discussions. Multigraphs are the graphs where there could be multiple edges between a pair of vertices. So for example, if you look at the vertices C and D, there are 3 edges between C and D. What kind of applications will need these 3 kinds of edges? So you can think of C as a particular location, D is another location on the map, and then there are 3 possible routes between C and D. Having different constraints, different costs, different distances, or travel times, or whatever we model on those edges. So multigraphs are also specialized types of graphs. So when we say, whenever we use the term simple graphs, that means that we are not talking about multigraphs, we are not talking about pseudographs. In other words, simple graphs don't include self-loops. They can't have multiple edges between 2 vertices. Okay, so this session, this particular slide set and this session is more on the terminology part. We are getting introduced to different terms, which we'll be using again and again as we go along in our graph theoretic journey. So as we talked about at the start, that edges can be possibly named explicitly, but the pair itself is a sufficient representation to name or represent an edge. So if you look at the leftmost edge, this is E1, this is same as AB. So A and AB are 2 endpoints of E1. And another term which we use is that A and B are immediately connected because they're directly connected with each other, so they are adjacent to each other. In other words, they are neighbors to each other. So adjacency or adjacent vertices is a common term which you keep on using as you go along. A and B are adjacent, same way C and B are adjacent, C and D are adjacent. A and D are not adjacent because there is no direct connection between them. They are not immediate neighbors of each other. And E1 is an edge which is incident to A and B. So an edge is incident to its endpoints. Degree is another important term. So degree of vertex is the number of edges incident on that vertex. So if you think of C, there are different edges which are incident on C. So for example, one edge is coming from A, another one is coming from B, third one is coming from D. So degree of C is 3. The number of edges which are incident on that particular vertex will give us degree of that vertex. And we'll use this notation, DEG of V or degree of V. So next ICP is that pause the video over here and figure out on your own that given an unseen some graph where we know size of vertices, the size of set of vertices and size of set of edges, what is the minimum and maximum possible degree of a vertex? So if you have figured it out, so minimum possible degree could be 0, which means that there's a vertex which is not connected with anyone else. And the maximum degree is n-1, which means that that vertex is connected with every other vertex. And over here, we are talking about simple undirected graphs. So degree of V ranges between 0 to n-1, both inclusive. You take a pause, figure out, look at this particular example, compute the degrees of all these 4 vertices. You might have figured them out. So let's do some of them. Degree of A is the number of edges which are incident on A. So there are 2 edges which are incident on A. One is E1, other one is E2. So degree of A is 2. Degree of B is also 2. Degree of D is 1. And degree of C is 3 vertices are incident on C. So its degree is 3. There's another property which we'll see later, but like if you add these total or add these all degrees, so 2 plus 1 is 3, plus 2 is 5, plus 3 is 8. So this 8 is sum of all degrees of the graph. This has a beautiful relation with something, and that is that this is 2 times cardinality of E. And if you focus on this expression, that the total degree is 2 times E, so number of edges over here in this particular example are 4. So 2 times 4 is 8. Why is it so? Because each edge which we are looking at is contributing twice in computing individual degrees. So this edge contributed once while computing degree of A. It contributed another time while computing degree of B. So one edge has been counted twice in degrees. That's why 2 times cardinality of E is the total degree of the graph. Now we are moving to the second type of graphs, which are called directed graphs, or sometimes we call them digraphs. So as the name suggests, and we have talked about these kind of graphs at the start, at the time of introduction. So you can see visually that each edge is a directed one, has an arrow on its head. So which means that this is E1 is an edge from D to A. So now if I write it as an ordered pair, so DA is an important thing. I can't write it as AD. This is not equal to AD. So if you recall our previous discussion, in the case of undirected graphs, these two things meant the same thing because order didn't matter. Now order is very important and set of edges have to be ordered pairs. So and more specifically, this set of edges is a subset of Cartesian product of set of vertices with itself. So the same term, order of the graph is number of vertices. We call them n. Size of graphs is number of edges. So question is, what is the maximum possible size of G of order n? Take a moment over here and pause the video. try to visualize some directed graphs. And they are simple directed graphs, which means we are not talking about multi-graphs or pseudographs. So try to figure out the maximum possible size of G. By maximum possible size of G means that at max, how many number of edges we can fit in a directed graph. If you have figured it out, so you might have come up with this kind of analogy that if we have, for example, we have 4 vertices. So this vertex is connected with everyone else because we are interested in maximum possible number of edges. So at max, this vertex can be connected to 3 more vertices. What about other vertices? So other vertices can also be connected at max with everyone else, which means 3 vertices. And the same analogy will apply to the remaining 2 vertices. So the total number of vertices are n. Each vertex can be connected with n minus 1 vertices at max, which means everyone else. And that expression will give us the maximum number of edges which we can have in a simple directed graph. We have talked about that pairs or each edge is an ordered pair. So for directed graphs, we distinguish degree in 2 forms. One is in degree, other one is out degree. So as the name suggests, in degree is the number of vertices which are incoming to that particular vertex. And the other side would be out degree, which means the number of vertices which are going out from that particular vertex. So as far as the notation is concerned, we put this superscript of this minus sign on degree or this function just to differentiate it from the out degree, or sometimes we write it as dv with this negative sign. So what is the minimum and maximum possible in degree of a vertex? So first think of the minimum possible in degree, and then think of the maximum possible. First think of minimum in degree, and then think of maximum in degree of a vertex. Take a pause. So if you had taken a pause, you might have figured out that, look at the top graph. So if we have a vertex over here, some new vertex, so the minimum in degree is that this vertex has an edge which goes from this vertex to some of the other vertices, and that there's no edge which is coming to this green vertex. So which means that the minimum degree is 0. And the maximum in degree is that if we have a vertex, some edge comes from a vertex, another edge comes from another vertex, another edge. How many edges can come from other vertices to this particular new pink vertex? They can come from everyone else. And everyone else means we are talking about, and sorry for the poor drawing. This we can have n minus 1 total incoming edges, so which means that degree ranges from 0 to n minus 1. Out degree is the number of outgoing edges from that particular vertex. It is noted as dg plus sign in the superscript. Take a pause, figure out the minimum and maximum possible out degrees of a vertex. Go with a similar kind of analogy as we did for the in degree of the vertex. So if you've done that, you might have already figured out that in degree and out degree, that their ranges are same. So when we have 0 out degree, that means that there is a vertex which does not have any outgoing edge. And the other extreme of maximum side is that there's a vertex which has an edge going out to every other vertex. So that will give us n minus 1. Okay, now we have many ICPs. Take a pause over here and solve all of them before moving forward. You would have taken a pause. Let me quickly solve some of them. So for example, if you look at 1411, so out degree of D is the number of edges going out from D. So if you focus on D, there is only one edge which goes out, so answer over here is 1. If you look at out degree of C, so there is an edge which is going out of C, there is another edge which is going out of C, so the out degree of C is 2. In degree of A, so if you look at A, there are 2 edges which are coming to A. So in degree is A, in degree of A is 2. In degree of B is also 2 because there are two incoming edges. So, and you can solve the incoming on your own. Okay, now, let's have a quick recall of pigeonhole principle, which we discussed last time. In a party of n people, some handshaking takes place. So a pair either shakes hands once or they do not shake hands. So the claim was that at least two people shook same number of hands. We talked about this principle and we showed that this how this claim is true. So pigeons are the number of people which are at least two. The possible number of handshakes can be from 0 to n minus 1. By 0 handshakes, we mean that there's a person who didn't shake hand with anyone. By n minus 1 would mean that there's a person who has shaken hand with everyone else. So these are possible, this is a possible range of handshakes. So over here, the possible number of handshakes is also n. Number of people which are pigeons are also n. So by just looking at these two facts, we can't really demonstrate the claim that at least two people shook same number of hands because both of them are same. Then like each people might be having different number of handshakes. So let's have a look on this, that whether it is possible or not. So first case is that someone shook n minus 1 hands, which means that there's a person in the list in the pool of people who has shaken hand with everyone else. If that person has shaken hand with everyone else, then there cannot be any person who would have 0 handshakes. So the remaining pigeons, 0 is now out of question for that conduct, for that case, and the remaining number of handshakes are n minus 1. People are n, so at least two persons must repeat same number of handshakes. If you think of the second case, if there is a person who didn't shake hand, there's a person who there is no person in the entire pool who had n minus 1 hands. Why is that possible? That if there's a person who didn't shake hand with everyone, then 0 is going to be there. But n minus 1 won't be there. And again, the cardinality of that possible number of handshakes will be n minus 1. So hence pigeonhole principle will be applicable over here. The reason we are like recalling it is that if you think of a graph, in any graph, there are at least two vertices of the same degree. So we have talked about the ranges of degrees. So we said that in a simple graph, 0 is the minimum possible degree, n minus 1 is the maximum possible degree. So the total number of degrees, the cardinality of this set is n, which means the total possible degrees are n. Total number of vertices are also n. So can this be a possibility that each vertex has unique degree? That's what we want to demonstrate, and we are going to bring in that handshaking lemma, which we've just revised from our previous concepts. So first case is that case number 1 would be that there is a vertex in the graph which has 0 degree. Right. So if there's a vertex with some vertex v has 0 degree. What does that mean? That means that this vertex is not connected with anyone. So then there can't be any vertex which will be having n minus 1 degree. So your remaining number of possible degrees are now n minus 1. And number of vertices are n. So at least two vertices should share the same degree. So its logic or its analogy is exactly same as that of fundamental handshaking lemma. We're just applying it in the context of graphs. Case 2 is that there is a vertex which is connected with everyone else. So if there is a vertex whose degree is n minus 1, which means that this vertex is connected with everyone else, what does that mean? That means that there is no vertex in the graph which will be having 0 degree. So minimum possible degree is 1. So all degrees from 1 to n minus 1 are going to be n minus 1. And hence, the possible degrees are n minus 1, number of vertices are v. So at least two vertices should share the same degree according to the pigeonhole principle. So this was the ICP. So I would strongly suggest that you use the same cases as we have just discussed on the slides and fill this ICP. Similarly, we can like use our previous fundamental principles we have been talking about in terms of counting. Uh, we can contextualize them in the case of graphs. So you might be able to recall this theorem that each collection of 6 people contains a group of 3 friends or a group of 3 strangers. So these two slides, this one and the next one, are exactly same as those which we had already discussed in combinatorics. So from a pool of 6 people, fix a person. Amongst how many people are remaining? Then out of those remaining 5 people, there will be at least 3 people who are all friends with A, or there would be at least 3 people who are all strangers to A. One of those cases must happen. So let's have a look on this, on the same thing in terms of graphs. So when we say 6 people, we're talking about 6 vertices. When we think of 6 vertices, so now consider these two cases. When we say a group of friends, that means that there is an edge from one person to some other person. I'm inserting some arbitrary edges, right? And group of strangers means 2 vertices are strangers if there is no edge. So absence of edge is notating strangers and presence of edge is notating friends. Now think of possibility, right? So fix any particular vertex. So let's say we fix this one. The remaining number of vertices are 5. Out of those 5, one of these 2 cases must happen. Among those 5 remaining vertices, there are at least 3 who are friends with A. So if you look over here, that first case does not fit on this particular example, right? So amongst the remaining 5, there are no 3 connected vertices with this pink one. But case 2 is true, right? So amongst the remaining people, there are at least 3 people who are strangers to A. So by strangers, we mean that there are no edges. So for example, I'm marking the absence of edges using pink. So this edge is missing, this edge is missing, and this edge is missing. So at least one of these 2 cases must have to be true. So if you think of the first case, that case can be broken down into 2 pieces. Amongst the 3 people who are friends of A, there are 2 who are also friends with each other, or all of the remaining people are strangers with each other, right? So you can draw this graph and analyze these cases. Amongst if we have case 2, amongst all those at least 3 people who are strangers to A, there are 2 who are strangers to each other, or there are all of them are friends to each other, right? So blue color over here represents friendships, and red text represents no friendship, or in terms of graphs, red ones means that there is no edge between those 2 vertices. Blue means that there is an edge between 2 vertices. In other words, we are using graphs to model the friendship. And this is just rewording of the same theorem that any graph on 6 vertices has 3 vertices or adjacent to each other, or they are not adjacent to each other. So not adjacent means that the edge between those 2 particular vertices is missing. Okay, now there is some fun part. Take a piece of paper and draw these 2 graphs. I'm going to explain that what kind of graphs we are looking at. Try to, in the first exercise, try to draw a graph of 3 vertices such that first vertex has degree 2, second one has degree 2, third one has degree 1. Once you're done with this thing, then draw another graph of 5 people. Everyone is friend with exactly 3 other people, right? Which means draw 5 vertices. Friendship is being modeled as edges. So each vertex should be having degree 3. So try to draw these 2 kinds of edges. It's written on slides that don't spend more than a minute on this problem, on each of the problems. So you can pause the video for the next 2 or 3 or 4 minutes of your choice. Strongly suggested don't move forward before trying them. And after you are done, then you can come back in a few minutes. But if you are like running out of time, uh, you may try for some extra seconds, but then like if you're facing difficulties, then come back. So if you have come back, you can spend the next 600 years on these two problems, and you'll never be able to draw those graphs. So that is an interesting observation over here, that why won't you be able to draw those kind of graphs? So let's try to build some analogy at this stage. So if you look at the first example, we are talking about three graphs. We are talking about three vertices. One vertex has degree 2. So when we add those two edges, so this vertex is now settled. How about this vertex? Its existing degree is 1. We want to make it 2. I have two choices. Either I reconnect it with the same graph, which I can't because we are talking about simple graphs, or if I try to connect it with this vertex, which still has degree 1, that will cause a problem because that third vertex will also be having degree 2 then, which I don't want to touch. So I don't want to change degree of the third vertex, which is this one. So I want to keep it 1 just to satisfy this part. So how to make its degree 2? So that means that there's an edge which goes nowhere. And such kind of graph cannot exist. Right? So it's just like thinking of that you have a friendship with question mark, which means that there is no person on the other end. So that means that there's no friendship. Or there's a road which is going from city A to nowhere. So that kind of graph intuitively cannot be built. Okay. Similarly, you can try to build a similar kind of analogy for the second example. So such graphs cannot exist. The sum of degrees of vertices in a graph is even. And this is the kind of thing which we talked about at the start of this session while talking about degrees. Why sum of degrees of vertices has to be even? The intuitive reason is that each edge contributes twice in computation of individual degrees. And when we take sum, so we are taking care of we are taking care of each edge twice. So whatever is the number of edges that gets multiplied with 2, so our right hand side is an even number. Or we can say that odd degree vertices, all those vertices whose degree is an odd number, their count must be even. So there could be two types of vertices. Some vertices have even degree. So there are some vertices whose degree is even. And then there could be some vertices whose degree is odd. So let's say X number of vertices are of even degree, Y number of vertices are of odd degree. So because degree is even, so each number which we are adding up over here X times, this sum over here on this side, total degree on the left hand side is going to be an even number, because sum of even integers is even. Now if you look over here, it's an odd degree. So X does not really matter. If X is even, our answer is even. If X is odd, our answer is even. What about the right hand side? Odd degree vertices means that each vertex on this side, on the right hand side, has odd degree. So we have to add some odd numbers. So if we add two odd numbers, our answer is even. If we add odd number of odd numbers, that gives us odd. So why it has to be even? Because it must be even. Why? Because sum of these two degrees is even. We know, that's what we know. So if one component is even, the other component must be even. In order to make this sum, the right hand side sum even, in order to make this sum even, Y must be even. Y is the number of odd degree vertices. So all these three versions of the same theorem mean the same thing. That is that number of odd degree vertices must be E1. Okay, as part of your ICP, you can argue that why these statements are equal and give a formal proof of handshaking lemma, the kind of stuff which we have just done on the slide. And similar kind of stuff is there in the case of directed graphs, that we have some for every edge which we have in the directed graph. So from one end, it contributes in the out degree. From the other end, it contributes in the in degree. And each edge is contributing twice in the total degree, once in degree, the second time in the out degree. So total out degree is same as total in degree of the graph, and that is essentially the number of edges. So use the lines which we have just discussed in our previous version, and you can demonstrate its proof as an ICP. So another type of graph is called weighted graph, which means that besides these two fundamental sets, which are building blocks of the graphs, set of vertices and edges, we are adding a third component in definition of a graph. So this W is notating a set of weights, or weight, we call it weight vector. So graph is now going to be weighted, which means that each edge is a weighted edge. Each edge is labeled with a number which represents weight of that particular edge. So besides V and E, W is cost or weight function. So where for each edge there is a real number which represents weight of that thing. So what could be the weight? So for example, if you are talking about some distance, could be length in terms of distance on the edge, could be airfare, could be toll, could be energy, could be cost, could be profit. So different things, depending on the kind of application which we have, we can model different, we can use weighted graphs to model different real world problems. So you can see this example as a weighted graph. There are many edges, vertices, graph is a directed one. But the new thing is that each edge has a number, which means this edge is a weighted edge. In general, the graph is a weighted graph. Weights can be positive, can be negative, because the function maps it to real numbers. So when to use positive weights, when to use negative weights, it totally depends on the kind of application which we are trying to model as graph. Attributed graphs are the graphs where each vertex is an object. So from your CS200 concepts, you are familiar with the concept of objects. So each object, so for example, if you think of a social network restricted to lumps, so each object contains some information about a person, a student, more specifically, gender, age, major, and some program code. So that is ethnicity. The fourth one, gender, age, major. So this is generic definition of attributes for the class node. And you're putting, you have a collection of nodes, and different nodes are connected with some of the other nodes, depending on the kind of friendships or connections or social interactions between those two particular nodes. Okay, so for today's session, we are now into the last but important discussion about graphs. The question arises that when we talk about graphs, this is a mathematical structure. Sometimes it looks quite fancy and attractive when you start thinking in terms of different operations or algorithms which we can apply on these graphs. So one possible way to store this graph in computer's memory is to use an underlying representation, which is called adjacency matrix. So adjacency matrix has somewhat very similar characteristics as that of a simple matrix. And as the name suggests, adjacency means that this matrix encodes which of the two vertices are directly connected with each other. So adjacent means direct connections between two vertices. Two vertices are adjacent if they are directly connected. By directly connected, we mean that there is an edge between those two vertices. So we fix an arbitrary ordering of vertices. One row for each vertex from the entire pool, one column for each vertex again from the pool. In other words, we are trying to create a matrix whose size is V cross V. So the matrix is filled with this notation. Aij means that ith row and jth column of the matrix A will be either filled with 1 or 0. So if there is an edge between vertex I and vertex j, then there will be 1. If there is no edge between vertex I and vertex j, then it will be filled with 0. In other words, we are creating an attendance sheet of edges, and that attendance sheet represents the underlying graph. We call this method of representing a graph, we term it as adjacency matrix. So let's try to understand this encoding. So if you look at this graph given on the left-hand side, so for example, okay, let's first count how many vertices are there. So they are labeled from A to H. So we have listed all of them from A to H on one axis, and we have listed all of them from A to H on the other axis as well. So that means that size of the matrix is cardinality of V times cardinality of V. So in other words, cardinality of V square is the size of the adjacency matrix. So now what kind of stuff is being put over there? So if you focus on the diagonal of the matrix, which goes this way. So the diagonal contains all zeros, which means that the graph is not a pseudo graph. There is no self loop in the graph. There's no edge from A to A, B to B, D to D, and so on. For some other possibilities, so for example, if we focus on F, so F is connected with E, F is connected with D, F is connected with G. So we focus on the row F. If you focus on row F, so there is 1 for D, 1 for E, 1 for G, and rest of the entries are 0 because F is not connected with any other vertex except these 3 vertices. So another smaller graph given its adjacency matrix A. Question, we've already figured it out. You can take a small pause to answer the question. How many entries are there in A? Same as size of the matrix, which is V cross V. Or if we are notating that number of vertices is n, so it's n square. How many ones are there? Think. The first answer is n square. How many ones are there? So that is an interesting observation. If you look at this edge E1, so there is a 1 from A to D over here, and the same edge is being counted from D to A. So for each edge, we have 2 ones. So number of ones are 2 times number of edges. Each edge is being marked twice for an undirected graph. So this is important. For an undirected graph, each edge is getting marked twice. How many zeros are there? So all remaining entries are 0. So total number of possibilities were n square. 2e of them are ones. All remaining entries are zeros. What are the diagonal entries? Diagonal entries represent self loops, and in this case, they are all zeros. How many ones are there in a row corresponding to vertex V? If I'm going fast over here, you can take pauses, solve these ICPs on your own, and then you can come back to my answers. How many ones are there in a row corresponding to vertex V? So for example, if we focus on this row, so we have 2 ones. What do they represent? They represent degree of that vertex. So for example, this third row is for vertex C. There are 2 ones because degree of C is 2. How many ones are there in column B? Sorry. How many ones are there in column corresponding to B? Again, the answer is same because the graph is undirected. And if you focus on a particular column, so for example, if you look at the third column, that means that there are 2 edges which are coming to C. So they are being counted twice. So again, it's degree of V for an undirected graph. The alternate representation is called adjacency list. So this is another equally good candidate. So one comment about adjacency matrix is that when we say adjacency matrix, that means that we are now more specifically talking about that how to store that graph in computer's memory. So in other words, that adjacency matrix is representing an underlying graph, but in computer's memory, that whole thing is that relationship between different vertices is being encoded as a matrix. And that's quite convenient from programming perspective because we know 2-dimensional arrays, and 2-dimensional arrays can be efficiently used to create an adjacency matrix and essentially represent a graph. And then you can apply different graph algorithms on that matrix to answer different kinds of questions. So the alternate category, the alternate representation is called adjacency list. So adjacency list is that which is like more sort of attractive for directed graphs, but we can also model undirected graphs using adjacency list. So we start with a list of all vertices. So all vertices are put over here in the structure. And if you look, if you are familiar with the notion of linked list, or even if you're not, so you can think of all these ones as pointers. And what do they represent? So from A to G, we have different pointers. And if you look at A, so A is connected with B and C. In other words, adjacent vertices of A are B and C. So and E as well. So what we do is that against A, we create a list of adjacent vertices. List order within this list does not matter, right? So an equally good choice could be CEB or CBE. Same way, if you look at vertex E, so it has no outgoing vertex. It does not have any adjacent vertex because it's a directed graph. So E is adjacent of some other vertices, but it does not have any adjacent vertex. So the list or the pointer of E does not point to anything. So this is an empty list. And G has one adjacent, which is E. So each list contains neighbors of that particular vertex, which is given in the first column. So this kind of representation is called adjacency list. So now we can analyze this thing, and we can have an idea of one small thing, that the total number of elements which we are putting over here are same as number of vertices. What are the total number of these elements? So these elements are only being inserted because they are connected with some vertices using some edges. So each edge is being put over here once. So if you have to notate, if you have to use adjacency matrix or adjacency list for a weighted graph, then we can add an additional attribute in the lists to notate weights as well, besides their names. So this the size of the object changes, and we add an additional attribute to store weights. In terms of weighted adjacency matrix, so instead of putting ones, we directly put those numbers which are weights of the edges. So which of those two representations is good? Which of them is not that good? So essentially, it depends on the kind of application which we are talking about. But in general, adjacency matrix is the one which requires n square bits. So if you have a like sparse graph, it means a graph of large number of vertices, but not that many edges. We'll be having a lot of zeros, additional zeros over here in the adjacency matrix. But in case of adjacency list, we might be having at max 2m or twice number of edges as the elements over here. So some of the queries might be addressed more efficiently in adjacency list. One small trade-off is that the adjacency list is little more tricky to implement in terms of computer programming. So this logarithmic notation is primarily an approximation that generally for sparse graphs, there are not like many edges in between. So our total number of total amount of memory which is required to store an adjacency list is relatively smaller as compared to adjacency matrix. Graph complement is another term. So we have been given a graph, set of vertices, set of edges. From a given graph, we can compute its complement. So complement contains same set of vertices, but edges change. And the kind of change which we apply on the edges. So if UV is a pair, which was not part of the original set of edges, we'll insert it in the complement. And then there's an if and only if, which means that if we have inserted an edge in the complement, it should be absent from the original set of edges and vice versa. So if you look at this graph of 4 vertices, so our number of vertices in the complement will remain 4, but all edges which were missing in the original graph will be inserted in the complement, and all edges which were present. So I'm just putting some missing edges over here for better understanding. So these edges, these pink edges were missing. So we add them over here in the complement. The green edges in the original graph have been removed from the complement. The complement contains same set of vertices as the original one. So all existing edges become non-edge and all non-edges become edges. Okay, try to formulate a mechanism or algorithm or piece of code or pseudocode that how to compute complement from adjacency matrix and adjacency list. So to try to figure it out on your own. So if you understood the complement concept, you should be able to come up with a mechanism that how you will be able to output complement of a graph given these two representations. Graph transpose is computed from a given graph. Again, the set of vertices remains same. Edges are changing. So if there was an edge VU in the original set of edges, it becomes UV, which means because both of them are ordered pairs, that means their directions are flipped. So the order of edges change. So vertices remain same and directions are changed. So if you look at the left side graph, this is the original one. This is what we call G. And the right hand on the right side, you can see G prime, which is transpose of the graph. Sometimes we write it as GT. So GT put in the superscript. So GT of the given graph is that all edges are there, but their directions have been flipped. That's called transpose of the graph. ICP is that how to compute transpose of the graph from adjacency matrix and adjacency list. Try to come up with an algorithm, code or pseudocode or sequence of steps. Subgraph of a graph. If you look over here, subgraph may not contain the original set of vertices. So the set of vertices in the subgraph is subset of the original set of vertices. Set of edges is also subset of the original set of edges, which means that we have a choice to drop some vertices and some edges. So there could be many subgraphs of a given graph. So if you look at the first leftmost graph, that is G, original graph. The right side two graphs are subgraphs of the original one. So the first one, the first subgraph, which is H1, this does not contain the vertex C, so that is absent, and then there are many edges. For example, the edge from B to E is also missing, so that's fine because edges have to be subset and vertices have to be subset. This is one possible subgraph. If you look at H2, so this does not contain vertex A, and this does not contain many of the edges which should have been there. So for example, this edge is missing, and this is also a subgraph. Subgraph is a component of the graph. So smallest subgraph could be an empty graph, and a graph is a subgraph itself as well. Induced graph is a type of subgraph which has an additional restriction, and that is that you can have a subset of vertices. You can have a subset of vertices, but in the edges which you have to put in inside that subgraph, all original edges which are between the set V prime must be preserved. That means that if you look at the original graph G, so in H1, we are saying that this is not induced. Why? We are fine with C. C can be removed and we don't have any issue. But the problem is that the vertices which we have selected are these four vertices, A, B, C, D. So there are some edges which are missing. So for example, edge between B and E is missing. So this edge cannot be missing if you're talking about induced subgraph. Induced subgraph can contain some of the vertices, but all edges which were in E amongst those V prime vertices, they have to be preserved. And the right side subgraph, which is H2, is an induced subgraph of the original one. So spanning subgraph is another concept. So it contains all original vertices and some of the edges are there, right? So if we look over here, the original graph contains 5 vertices. So both of our spanning graphs contain 5 vertices, but on edges we have a discount and that's allowed. We are fine with that. So some edges can be removed. So a graph is a spanning graph of itself, and we can create new spanning subgraphs where we can possibly drop some of the edges. So that's it for today. So we will follow the same protocol of ICPs as that of the previous recorded session. You will have to solve all ICPs and submit them on LMS. Thank you very much for your attention.